In this video, we are going to discuss geometrical isomerism in cycloalkenes. What exactly we are going to do here is, in case of these cycloalkenes, the double bond of cycloalkene, whether it is a geometrical center or not, we have to decide. Let us complete the lecture in three particular points. The first one, cycloalkenes up to 6 carbon atoms, cycloheptene and cycloalkenes having minimum 8 carbon atoms, 8 or more than 8 carbons. In case of cycloalkenes up to 6 carbon atoms, if you see the orientation of double bond, only cis orientation is possible, but trans orientation is not possible. Cycloalkenes up to 6 carbon atoms, cyclopropene, cyclobutene, cyclopentene, cyclohexene. If you see, in all these cycloalkenes, orientation of double bond, only cis orientation is possible. If you see the arrangement of hydrogens are same side to the double bond, therefore this orientation is said to be cis orientation, but a trans orientation is not possible. Why trans orientation is not possible? Let me explain with the help of a cyclobutene. In case of a cyclobutene, whenever you are writing the structure, always we write this structure. That means by default you are writing cis orientation. If you want to write a trans orientation, so this is a CC double bond. So here this is one double bonded carbon, this is another double bonded carbon. These are the two double bonded carbons. Hydrogens must be opposite side. So here this is the hydrogen and this is the hydrogen. And this double bonded carbon is attached to CH2 group. This is also attached to CH2 group. So in that they have to be oriented opposite side. So here this is a CH2 group, this is a CH2 group. So when these CH2 groups are oriented opposite side to the double bond, so here CC bond formation, you see it is highly difficult. Size of the ring is less, only 4 carbon atoms are present between these two CH2 groups. This is a CH2 group, this is a CH2 group. You can see they are opposite side to the double bond. Between these two carbons, CC single bond formation is very difficult. This is highly rigid, this is highly unstable, huge amount of bond angle strain. Therefore, cyclopropene, cyclobutene, cyclopentene, cyclohexene. Cis orientation is possible, but trans orientation is not possible. By default, it exists in a cis form. For example, let me take one more example. Whenever you write cyclohexene, by default you write this is the structure, this is the orientation generally we write. If you see the orientation of two hydrogens, they are same side. If you want to write the trans configuration, so these are the two double bonded carbons, sp2 carbons. You can see this is sp2 carbon, this is sp2 carbon. Your intention is writing trans configuration, here hydrogen and here hydrogen, they are opposite side. This is a CH2 group, CH2 group, CH2, of course this is also CH2, and here CH2 group, and this is a CH2 group. One more CH2 group, here also one more CH2 group. Like this, even in 6-membered ring, trans configuration is not possible. That is highly unstable, that will suffer from bond angle strain, huge amount of rigidity. Therefore, cyclohexene also, it exists only in cis configuration. That is the first point. In case of cycloheptene, it can accommodate double bond in cis and trans orientation, cycloheptene, but trans is highly unstable at room temperature. At room temperature, trans is highly unstable. Therefore, we have to rule out, we have to discard even cycloheptene. So, from the first and second points, we can conclude that from cyclopropene to cycloheptene, the double bond is not a geometrical center. If you are saying it is a geometrical center, it has to have cis form and trans form, but they are having only cis configuration. Trans configuration is not possible, that is highly unstable. Therefore, cyclopropene, cyclobutene, cyclopentene, cyclohexene, cycloheptene, we have to simply say geometrical isomerism is not possible. When cyclooctene, if there are minimum 8 carbon atoms, 8, 9, 10, in all those systems, both cis and trans configurations are possible, both exist at room temperature. Therefore, from cyclooctene to higher members, double bond will be geometrical center. This is the key point you have to remember. Whenever you are dealing with cycloalkenes, what is the statement you have to remember? If size of the ring is 8 or more, then double bond will be geometrical center. Cis and trans configuration is possible. Whether it is a cis trans or EZ, geometrical isomerism is possible. For example, in case of cyclooctene, you can see totally 8 carbon atoms and hydrogens are arranged opposite sides. Hydrogens are arranged same side to the double bond. Therefore, it is said to be cis configurations. If you want to write the trans configuration, in case of a trans configuration, you can see here we have hydrogen, here we have hydrogen. For the sake of convenience, I will write, you just observe the two double bonded carbons, sp2 carbons, hydrogens are opposite side. First you write like this, and here 1, 2, 3, 4, 5, 6. 8 minus 2, that is 6 carbon atoms. So this is 1, 2 and 3. Even here 1, 2 and 3. Now the size of the ring is more and it can exist in trans configuration also. So cyclooctene and higher members, more than 8 carbon atoms, double bond will be geometrical center. You can see totally there are 10 carbon atoms and here hydrogens are opposite side. Therefore, this is said to be trans configuration, and here hydrogens are same side. Therefore, it is said to be cis configuration. Many students, when they are learning the concept first time, when they are asked to answer the relation between these two, simply they say they are positional isomers, but in fact they are not positional isomers, they are actually geometrical isomers, configurational isomers, stereo isomers, cis and trans isomers. So here these are cis and trans isomers, they are stereo isomers. And what are the different configurations we use to represent geometrical isomers of cycloalkenes? Yes, you can use a cis trans configuration. You can also use a EZ configuration. Same thing, if it is AB type of structure, AD type of structure, two double bonded carbons, if there is at least one common group, then we have to go for cis trans configuration. If there is no common group, that is AB DE structure, no common group. These are the groups of one double bonded carbon, these are the groups of another double bonded carbon. In that situation, we have to use a EZ configuration. So let us take some examples. Here, the size of the ring is definitely greater than 8. So this is not a geometrical center. If you see here, both are hydrogens. So this is not a geometrical center, but this is a geometrical center. And here this is having trans configuration. This is also geometrical center. Here this is having cis configuration. Now you can see the next example. The number of carbon atoms, if you want, you can count here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon atoms. And in case of these 10 carbon atoms, if you see here hydrogen like this, here hydrogen like this. So around this double bond, you can see hydrogens are opposite side. Therefore, this configuration is a trans configuration. Even the next one, You can see chlorines are opposite side, therefore this is said to be trans configuration. In the next example, more than 8 carbon atoms are present. You just see the orientation, write hydrogens properly. It is sp2 carbon. Try to maintain 120 degrees, but it here exactly it is not 120, that is nearer to 120. Here one hydrogen, here one hydrogen. Don't write hydrogen here. You just see, try to maintain 120. Hydrogens are again opposite side, so therefore this is said to possess trans configuration. Next one, here hydrogens you can see they are same side, therefore this is having cis configuration. And here you can see more than 8 carbon atoms, here one hydrogen, here one hydrogen. Hydrogens are opposite side, therefore this is having trans configuration. And some more examples, let us do it fast. So here this is a hydrogen, this is a hydrogen. Hydrogens are same side, cis configuration. Hydrogen, hydrogen, hydrogens are opposite side, therefore it is a trans configuration. So here next example, you can see hydrogens are same side, therefore it is having cis configuration. Even here hydrogens are same side, this is also having cis configuration. In fact, one more example, hydrogens are same side, this is also having cis configuration. So this is about geometrical isomerism in cycloalkenes. So the key point here is, in case of cycloalkenes, this double bond is geometrical center if the ring contains 8 or more carbon atoms. 8 or more carbons. Cyclooctene, cis and trans both are possible. Cyclononene, yes possible. Cyclodecene possible. But cyclohexene, only cis form. When it is having only cis form, we should not say it shows geometrical isomerism. If you want to say the molecule shows geometrical isomerism, you should be able to write a cis form and a trans form, otherwise E form and a Z form. So this is about geometrical isomerism in cycloalkenes. Thank you very much.